In the previous video, we learned a method to find a basis for a span. We'll apply this method in example 7.4.4. I'm going to take S to be the span of these four vectors in R4. Let me call them V1 through V4 to save some time. I want to find a basis for S. All right, so let's go back to the method here. If I want to find a basis for a span, then what I have to do is I have to reduce the matrix H that I get from including the vectors as columns. So here that would mean looking at 1, 4, minus 2, 3, minus 4, 16, 8, minus 12, 2, 0, 1, 1, 1, minus 12, 8, minus 7. So I need to reduce this to, let me go to RREF just because that's going to make the next few questions easier to solve. So I'm getting 1, 0, 0, 0, then minus 4, 0, 0, 0, 0, 1, 0, 0, and minus 3. All right, so I've reduced H. Then B contain only the vectors whose columns correspond to leading ones. So let's see. I'm going to look at leading ones. I have these two. They correspond to these vectors. So my basis will be V1, V3. That should be 1, 4, minus 2, 3, and 2, 0, 1, 1. All right, that's it. In B, we're asked to write each of the vectors as a linear combination of the basis. So each of these is in S, so we can write it as a linear combination. So I need to write V1 as a linear combination of V1, V3. Well, that one is a bit silly. Same thing for V3. Those are not super interesting, but of course they could be written as well. Now what's interesting is I have two vectors that are no longer in my sets of generator. I have V2 and V4 that I got rid of. So V2 I need to write as something V1 plus something V3, and same thing for V4. I need to write it as something V1 plus something V3. Now if I go back to the method, each free column in the reduced RREF matrix gives the coefficients necessary to write the corresponding vector as a linear combination of the elements. So I use these columns to choose my basis. The remaining columns tell me why the other vectors are not needed, why they're redundant. And so if I look at this vector, V2, I can see here that it's minus 4 times the first. Right? That relationship between the columns is preserved throughout the reduction. So I don't need V3, but I need minus 4 times V1. For V4, I need to look at this column here. I'm going to use minus 3 times my first leading one, so that's minus 3 times V1. And I'm going to need twice the second leading one, so twice V3. All right, so this relationship is true here, and so it was true at the start. The fourth column is minus 3 times the first plus 2 times the second. The fourth column is minus 3 times the first plus twice the second. All right, now I'm asked to find a different basis for S. That's interesting. So I found a basis, V1, V3, and that's the basis given to me by the method. Now I could try to find a basis some other way, or I could apply the method slightly differently. Something that I used was the order of these vectors, right? I chose in which order to put them in the matrix, but I could choose it doing this in a different way. So what if I put What if I wrote them backwards? I mean, you could try any order you want. You're going to get a basis, but let me put V4, V3, V2, V1. Leading ones tend to be on the left, and so in this case, I would expect to keep probably V4, right? All right, so let's see what I get. If I put them in, I'll get, here's V4, then I want V3, I want V2, and I want V1. All right, so I've reduced this one for you as well. What I got was 1, 0, 0, 0, 0, 1, 0, 0. Notice that this is not going to be part of the original matrix. When you switch the order, the row operation you're going to do is going to be very different, because the leading ones will be somewhere else. All right, so I get a completely different reduction, and here are my leading ones, and so in this case, what I'm going to keep, blue, my B is not going to be V1, V3, that's going to be V4, V3. So there were two reasons I wanted to do this example. The first one is to show you what the last method looks like, both to find a basis and also to write the redundant vectors as the linear combinations of the basis vectors. But also I wanted to show that I could use different sets of vectors as a basis for the same span. So as the last example shows, sorry, I'll zoom in. A span does not usually have a unique basis. In fact, any non-trivial span will have infinitely many different bases. So it's not just this particular case. If I start with most spans, I'm going to have infinitely many different bases. All right, so I want to do this for R2. I want to give 3 bases for R2, and I'm told no justification necessary. All right, so I just need 2 vectors that are not parallel. And of course not 0. And we've already seen 1, 1, 0, 0, 1, that works. I just need non-parallel vectors, so what else could I do? I could keep 1, 0, but then 1, 1 maybe? That would work, they're not parallel. So I could use 1, 0, 1, 1. What else? It's one of the cases where you have so many possibilities. Let me do this. Yeah, something like that would work. B3, that's minus 1, 1, and minus 1, minus 1. But you could see, I mean, there's so many ways of doing this. Here are 3. I could come up with 20. It'd be pretty boring for you, so I'll stop here.